Welcome, this is Dr. Jen. Today we're going to talk about tricky infinite limits. Basically we're going to talk about some infinite limits that don't fit the normal patterns, but we can figure them out anyway. We have to reason a little bit and then we'll why don't we look at them and see what happens. Here's my first one. It looks kind of like a rational function. It is a ratio, but that's an e to the x. It's not a x squared or something like that. This is not a rational function, so the rules for rational functions don't directly apply. However, as x goes to infinity, the same concepts apply. Here's the concept. If x is getting really large, not like to a number, but to infinity, or minus infinity works too, you have to identify which is the most significant term, or what terms are on par with each other. If x is really big, 4 versus e to the x, well, the e to the x becomes infinitely huge. It's the only term that's really significant. Likewise, in the bottom, it's the only term that's really significant. As x goes to infinity, those are the only ones that matter. So this limit is the same as the limit going to infinity of, well, we still need the minus in front of it, minus e to the x over e to the x. So what do we get? Well, the e to the x's cancel out. This one is minus 1. If you don't like that, you could try it with a table, but I think this is easier. However, remember, this is not a rational function. So let's try, instead of going for infinity, let's try for minus infinity. Now, what do we have? What is the most significant term? Well, if you start plugging values of minus infinity are really small into e, e to the minus a really big number is close to 0. So now the significant term has moved. On this side, the significant term is this 4. Likewise on the bottom. So this limit is the same as the limit as x goes to minus infinity of 4 over 4. Notice how it's different. That's 1. This graph, if you graph this graph, has 2 horizontal asymptotes. It looks like this. At 0, let's see, 3/5, so it'd be something like this. How do you graph functions like this? That's for a much later topic. But the 2 horizontal asymptotes are things we can compute. Let's move away from the e's. Well, maybe not yet. Here's a trickier one. This one looks like the other one, but let's be very careful. Let's identify, as x goes to positive infinity this time, e to the positive, that makes this the significant term. E to the positive, that makes that the significant term. So this is going to be the limit as x goes to infinity of minus 2 e to the x over 3 e to the 2x. Now notice, they don't directly cancel out. They can partially. E to the 2x is e to the x times e to the x. So we do have some cancellation. So if x goes to infinity of minus 2 over 3 e to the x. That's all the cancellation I can do. So now I have to stop and think. If x is getting really big, what's happening to this? This leftover e to the x is getting really big. So the bottom of this fraction is getting huge. Top is not. Top's not getting any bigger. When the fraction at the bottom gets really big, that means this whole thing is going to 0. So notice, when you have exponentials, if they're the same as on the top and bottom, they can help cancel. If they're not the same, be very careful. Now, moving on from exponentials, let's do radicals. Radicals are another really tricky thing. Square roots are not usually the favorite function of a typical student, but we can work this out. Again, using the idea of the largest piece. So as x goes to minus infinity, well, the bottom is easy. There's only one term. So it's going to just be limit. X is going to minus infinity. On the bottom is still 2x. What about the top? Well, the square root throws us off. But that's all there is. So within the square root, only the x squared term is going to make a difference. So this is the square root of x squared. Now you may be tempted to simplify that. And that's a good thing. You should simplify that. But don't simplify it wrong. Square root and squaring are inverse ideas, but they're not literally inverse functions because squaring makes a positive. When you square root, you always get positive. Regardless of whether we're going to positive or negative, the top is going to be positive. And since we're in the negative zone, going towards minus infinity, this is the absolute value of x. Now that may be enough to make you unhappy. But notice, there's 1 power of x on top, there's 1 power of x on the bottom. They will cancel. But the top's always positive, the bottom's always negative. If you think about that, they will cancel, but that's positive, that's negative. The canceling makes a net negative. There's a 2 also. The net effect for this very tricky one is minus 1/2. Now, if that's not sitting well for you, you can also confirm it by taking a limit with a table. Take some values, plug them in. It should come to it. And if that's not enough, let's try one trickier one. What makes this one trickier? Well, take a look at this. This is going to where? As x goes to infinity, where's the x going? Infinity. Where's this going? Infinity. So we have a form, it's one of the indeterminate forms. It means we can't evaluate. What is infinity minus infinity? Well, we don't know. So we have to figure this out. Now, up till now, I've always said, only look at the biggest power. So you might be thinking x squared here is only the biggest piece. Unfortunately, because we're going to cancel out a big piece too, we can't just ignore the smaller pieces. This is different than every other one so far because we have 2 things that are both blowing up and are both important, and you can't say one is bigger than the other. So when you have that case where they're both, well, what is the power here effectively? X squared square rooted, that's 1 power of x, that's 1 power of x. Since they're both on equal power, we have to consider every bit. And how do we get to those bits? Before, we did it just by ignoring everything else. Now we can't ignore, so how can we access that? We do it with conjugates. So I'm going to multiply by the conjugate here. The conjugate is the same thing, but with an opposite plus or minus sign in the middle. So we go x squared plus x. And I don't want to change anything, so I'm multiplying that on the bottom also. And if you don't like the idea of there being a bottom not to begin with, make that over 1. And now we have a bottom of a fraction. Let me multiply everything through. The bottom is x squared plus x, and then add x. Over here, this term and this term, multiply together. X squared plus x. The middle terms, minus those 2 together, plus those 2 together. Those cancel. The reason we multiply by conjugates is so the middles will cancel. But then we also have minus x times x is minus x squared. And hopefully now you can see minus x squared, x squared. Those pieces cancel. And what do I get on top? An x. That's all that's left. On the bottom, square root of x squared plus x, and then plus x. Now remember how I said you can't, if we're having a difference, we have to keep all of the bits. If this is on par with this and we're subtracting them off, we have to keep all the bits. Well, what's different? We're not subtracting anymore. Now we're adding. So they're not going to cancel each other out in any way, so we no longer care for those extra little bits, that extra x. We can get rid of it because it's not going to cancel out. The hardest part with these blowing up things where they blow up is if you cancel out the biggest piece, you have to keep the second biggest piece too. But if you're adding on, you no longer need that. So I have an x, what's this? Square root of x squared plus x. Because that piece no longer matters, because I'm adding. They're not going to cancel out at all. Now remember how I said this is really the absolute value of x? It is. It's not x, it's the absolute value of x. But when x is positive, the absolute value of x is x. So for us, I'll write it as the absolute value of x, but for this particular limit, that's just x. I have x divided by 2x. X divided by 2x is 1/2. I know that's a lot of tricky limits. They're hard to do. That's why they're the tricky ones. But with some practice, you can get it. This is Dr. Jen.